So, a couple of things that I'll talk about here. Just sort of. This is abstract, actually. How do you measure a rate? Well, you do an experiment. You always got to do an experiment to measure a rate. There's like no other way to do it. And then you measure something versus time, right? So in this case, we measured the length the slug traveled versus time, but we could calculate the change in something versus the change in time. The other way to do it is collect data at different times and calculate the slope of a graph. Then you're using all the data, right? So we'll talk about that. It's called the instantaneous. And this is known as the average. I didn't actually put the A in there, did I? And this is going to be average rate, and this bottom one is going to be the instantaneous rate. So what do I mean by calculate the slope on a graph? So you know, like if you get a graph that looks like this, right? And then you have data points that look like this. And you want to calculate the slope, right? Well, you can draw a line through the data and well, you can draw a line through the data. Well, okay, let's just pretend that's a actually I got an idea. Look, it's a perfect fit. Now, you can draw a line through the data, and then what you can do is you can calculate the slope by picking 2 points off of the line. And the reason that you do that in math, generally speaking, is because it's more accurate to do that. You're using all of your data. You have a little bit more robustness in the calculation. You're not depending on the slope just between 2 points. Now, in this class, what's going to happen, and again, I'll do some of this with you, you're going to have a graph that looks like this. It's going to be curved. So then the question is, how do you calculate the slope of a curve? Because, right, by definition, it's a curve, so the slope is changing all the time. So what you have to do is you have to draw a line. Ooh, I don't know what happened there. That's parallel. So normally you would draw that to touch, but you can see how my drawing skills are. But it's also, I wanted to show you something that you want to draw the line parallel to the point that you want the slope of. So, you know, I want the slope right at that point. And so I draw a line that's parallel to the slope at that point, and then I take 2 points off this line. And this is known as the instantaneous slope, because what you're doing is you're calculating the slope right at that point. It's higher to the left and lower to the right, right? So that's what we mean by instantaneous. It's just that it's the point at one time, and it's not necessarily, because you have this curve drawn through it, it's not necessarily a place where you actually have a data point. Okay, so there's instantaneous rate and there's average rate. So here's some just general ideas about reaction rates as they relate to reactions. Okay. First is the concentration of reactants is always the highest at the start of the reaction. I think that makes sense. But as the reaction goes, right, the reactants are used up, and so their concentrations drop off. And because concentration is an important part of how fast a reaction goes, the rate slows down. All right, now think about what that means, like in a graph, because I actually haven't shown you like a real graph yet. All right, what does that mean? Well, the slope, if the rate's the highest at the start, that means the slope will be the highest at the start. Like, I don't know how I can make, yeah, well, like, slope will be highest at the start. Maybe it looks better that way for you. I don't know. I can't tell which way it looks best to you, honestly. The highest at the start, and then over time as it goes, it's going to go lower and lower. It probably won't drop to zero, actually, although it might not be measurable changes, but in theory, reactions slow down over time. They just keep getting slower and slower and slower, just because the concentration goes down. Now, that's not always the case, but it is generally the case that you see that, okay? Now, the other thing to think about is as the reaction goes, you begin to make product. So every bit of reactant that gets used up, right, begins to generate product. So in principle, even though we're talking about reactants getting used up during the course of the reaction, oftentimes it's the product that we measure, because the product starts out at zero, and it turns out zero is really easy to measure. It's just zero, right? And then it increases over time, and so you can measure the products coming out as well as the reactants going down as a way of measuring the reaction rate. Okay, so a little bit of like background again. This is how you would do the average versus the instantaneous rate. This is just a nicer slide, right? So this graph is showing two measurements of the instantaneous rate. So what they did, and this is honestly not what I would have done, but what they did was they drew a tangent line. This is my tangent line. This is from your book. And on the curve to this point, because this is where they wanted to measure the instantaneous rate of the reaction, and then they drew this line, and then they measured the rise and the run, right? So this red line is for the product that's formed, and this green line is for the reactant. And I know that because you can look in your book. There's a reaction right there. I know that because there's the reaction right there. But I also know that because the reactants go down generally, the products go up. So if I wanted to calculate the reaction rate, okay, or the rate, sorry, not the reaction rate. Oh yeah, that all says reaction rate. I'll have to change that. But if this should just say rate, get rid of the reaction. Turns out the reaction rate and the rate aren't always the same. So if I want to calculate the rate, and this is the instantaneous rate, I would say rate equals, and then they calculated these parts for me. So this is going to be, I'm going to do this one down here. Negative 0.28, right, like that. And then it's divided by, and then they did it for 40 seconds. They measured that out as 40 seconds. And the units on this axis are molarity, so it's like that. And so the rate comes out to be 0.28 divided by 40. And that'll come out to be like 7.0 times 10 to the minus third. And they got a negative sign here. And the negative just means it's going down, okay? Now, let's do the calculation for the HI, right? So this is the rate for, I think it was H2, yeah, H2. We're going to do the rate for HI. So that's going to be, again, measuring 0.56, right? And then that's units of molarity. And then I'm going to do, 40 seconds again. And you notice that it's 0.56 positive because it's increasing, right? And so that's going to come out to 1.4 times 10 to the minus 2. And I'm guessing, let's go ahead and pull the calculator out, and I'll tell you why I think it's that in a second. So that's going to be 0.56, so 0.56 divided by 40. Yeah, 1.4 times 10 to the minus 2. I just did the scientific notation conversion in my head. The units for both of these are in molarities per second. Molarities per second. Okay, good. All right, so this is how we measure rate. The instantaneous rate is used by taking a tangent line. If you wanted the average rate, then what you would do is you would take the slope between 2 points. So you would actually use, let's say, those 2 data points and calculate that. And I'll show you how to do that on another set of data. Okay, so let's talk about this a little bit. Why are the numbers different? Well, they're different because of stoichiometry, right? There's a 2 here. And the HI gets produced twice as fast as the H2 gets used. And the result is, right, the slope is twice as big. You could see that, that's minus 2. You could see that really easy if you just wrote this as 10 to the minus third here. So I'll do 10 to the minus third, which means I have to shift it over to the right. So it's going to be 14 times 10 to the minus third molarities per second. And now that I have them in the same exponential scientific notation, You can see 14 is twice 7, so it's going twice as fast just because the stoichiometry dictates that it would go twice as fast. All right, so this is just some examples, and the data is on the next slide, but I figured I just leave that on the next slide. Originally, it was in front of the graph, but I think you don't need to see the data actually to do this. But uh, okay, so this is average rate calculation. I forgot to put that on the slide. Average rate. And what's the average, how the average rate is calculated that's different than the instantaneous rate is you just use the data points. So you'll see in this, well, maybe you do need to see the data. For A, the concentration is 1 millimolar, so that's 1 times 10 to the minus third molar, and then 0.74 millimolar, right? So to calculate the rate, it's 0.74 millimolar minus 1 millimolar divided by the change in time. And so your change in time is 0 to 10. So it goes from 10 seconds minus 0. So this is concentration 2, and this is concentration 1. This is T2, and this is T1. And this is the rate that you get, right? And then over time, right, we're going to calculate. So this is the initial rate, and then we're going to calculate this final rate. And the final rate is just the last 2 data points. It's crazy how many people struggle with just terms in here just because, and if it wasn't that it was kinetics, you'd be like, oh yeah, of course that's what that is. But for some reason in kinetics, there's so many terms that are thrown at you that are new. When somebody says just measure the initial rate, you're like, what's that, right? Anyways, it's the initial rate. It's the first 2 data points. The final rate would be the last 2 data points, right? Anyways, what you're going to do then is calculate. You'll get negative 2.6 times 10 to the minus fifth, right? And then if you go down here and you recalculate the rate, this is after 60 seconds, somewhere between 50 and 60 seconds. It's negative 6 times 10 to the minus 6. So it's actually a smaller number. And in a sense, you can just see it here. The slope is steeper here than it is here. And that's a result of the rate of the reaction going down as the concentration goes down. So that's why the little notes there, it's kind of a giant note. The concentration can affect rate. And this is a graph showing how you measure average rate. If you wanted to calculate other rates from this data, let's say example you want to do for B, all the data for B is here for you to do that calculation, okay? And if you try it and you're not sure if you're doing it right, just ask me and I'll help you out with that.